Describing performance. Once you have described the load on your system, you can investigate what happens when the load increases. You can look at it in two ways. Figure 1-4, illustrating mean and percentiles, response times for a sample of 100 requests to a service. When you increase a load parameter and keep the system resources CPU, memory, network bandwidth, etc. unchanged, how is the performance of your system affected? When you increase a load parameter, how much do you need to increase the resources if you want to keep performance unchanged? Both questions require performance numbers, so let's look briefly at describing the performance of a system. In a batch processing system such as Hadoop, we usually care about throughput, the number of records we can process per second, or the total time it takes to run a job on a dataset of a certain size. Roman 3 in online systems, what's usually more important is the service's response time, that is, the time between a client sending a request and receiving a response. Latency and response time. Latency and response time are often used synonymously, but they are not the same. The response time is what the client sees. Besides the actual time to process the request, the service time, it includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which it is latent, a waiting service. Even if you only make the same request over and over again, you'll get a slightly different response time on every try. In practice, in a system handling a variety of requests, the response time can vary a lot. We therefore need to think of response time not as a single number, but as a distribution of values that you can measure. In Figure 1-4, each gray bar represents a request to a service, and its height shows how long that request took. Most requests are reasonably fast, but there are occasional outliers that take much longer. Perhaps the slow requests are intrinsically more expensive, for example because they process more data. But even in a scenario where you'd think all requests should take the same time, you get variation. Random additional latency could be introduced by a context switch to a background process, the loss of a network packet and TCP retransmission, a garbage collection pause, a page fault forcing a read from disk, mechanical vibrations in the server rack, or many other causes. It's common to see the average response time of a service reported. Strictly speaking, the term average doesn't refer to any particular formula, but in practice it is usually understood as the arithmetic mean. Given n values, add up all the values, and divide by n. However, the mean is not a very good metric if you want to know your typical response time, because it doesn't tell you how many users actually experience that delay. Usually it is better to use percentiles. If you take your list of response times and sort it from fastest to slowest, then the median is the halfway point. For example, if your median response time is 200 ms, that means half your requests return in less than 200 ms, and half your requests take longer than that. This makes the median a good metric if you want to know how long users typically have to wait. Half of user requests are served in less than the median response time, and the other half take longer than the median. The median is also known as the 50th percentile, and sometimes abbreviated as P50. Note that the median refers to a single request. If the user makes several requests over the course of a session, or because several resources are included in a single page, the probability that at least one of them is slower than the median is much greater than 50%. In order to figure out how bad your outliers are, you can look at higher percentiles. The 95th, 99th, and 99.98 percentiles are common, abbreviated P95, P99, and P999. They are the response time thresholds at which 95%, 99%, or 99.9% of requests are faster than that particular threshold. For example, if the 95th percentile response time is 1.5 seconds, that means 95 out of 100 requests take less than 1.5 seconds, and 5 out of 100 requests take 1.5 seconds or more. This is illustrated in Figure 1-4. High percentiles of response times, also known as tail latencies, are important because they directly affect users' experience of the service. For example, Amazon describes response time requirements for internal services in terms of the 99.98th percentile, even though it only affects 1 in 1,000 requests. This is because the customers with the slowest requests are often those who have the most data on their accounts because they have made many purchases, that is, they're the most valuable customers. It's important to keep those customers happy by ensuring the website is fast for them. Amazon has also observed that a 100 ms increase in response time reduces sales by 1%, and others report that a 1-second slowdown reduces a customer satisfaction metric by 16%. On the other hand, optimizing the 99.99th percentile, the slowest 1 in 10,000 requests, was deemed too expensive and to not yield enough benefit for Amazon's purposes. Reducing response times at very high percentiles is difficult because they are easily affected by random events outside of your control, and the benefits are diminishing. For example, percentiles are often used in service-level objectives, SLOs, and service-level agreements, SLAs, contracts that define the expected performance and availability of a service. An SLA may state that the service is considered to be up if it has a median response time of less than 200 ms, and a 99th percentile under 1s. If the response time is longer, it might as well be down, and the service may be required to be up at least 99.9% of the time. These metrics set expectations for clients of the service and allow customers to demand a refund if the SLA is not met. Queuing delays often account for a large part of the response time at high percentiles, as a server can only process a small number of things in parallel, limited, for example, by its number of CPU cores. It only takes a small number of slow requests to hold up the processing of subsequent requests, an effect sometimes known as head-of-line blocking. Even if those subsequent requests are fast to process on the server, the client will see a slow overall response time due to the time waiting for the prior request to complete. Due to this effect, it is important to measure response times on the client side when generating load artificially in order to test the scalability of a system. The load-generating client needs to keep sending requests independently of the response time. If the client waits for the previous request to complete before sending the next one, that behavior has the effect of artificially keeping the queues shorter in the test than they would be in reality, which skews the measurements. Percentiles in practice. High percentiles become especially important in back-end services that are called multiple times as part of serving a single end-user request. Even if you make the calls in parallel, the end-user request still needs to wait for the slowest of the parallel calls to complete. It takes just one slow call to make the entire end-user request slow, as illustrated in Figure 1-5. Even if only a small percentage of back-end calls are slow, the chance of getting a slow call increases if an end-user request requires multiple back-end calls, and so a higher proportion of end-user requests end up being slow, an effect known as tail latency amplification. If you want to add response time percentiles to the monitoring dashboards for your services, you need to efficiently calculate them on an ongoing basis. For example, you may want to keep a rolling window of response times of requests in the last 10 minutes. Every minute, you calculate the median and various percentiles over the values in that window and plot those metrics on a graph. The naive implementation is to keep a list of response times for all requests within the time window and to sort that list every minute. If that is too inefficient for you, there are algorithms that can calculate a good approximation of percentiles at minimal CPU and memory cost, such as forward decay, T-digest, or HDR histogram. Beware that averaging percentiles, for example to reduce the time resolution or to combine data from several machines, is mathematically meaningless. The right way of aggregating response time data is to add the histograms. Figure 1-5. When several backend calls are needed to serve a request, it takes just a singly slow backend request to slow down the entire end-user request. Approaches for coping with load. Now that we have discussed the parameters for describing load and metrics for measuring performance, we can start discussing scalability in earnest. How do we maintain good performance even when our load parameters increase by some amount? An architecture that is appropriate for one level of load is unlikely to cope with 10 times that load. If you are working on a fast-growing service, it is therefore likely that you will need to rethink your architecture on every order of magnitude load increase, or perhaps even more often than that. People often talk of a dichotomy between scaling up, vertical scaling, moving to a more powerful machine, and scaling out, horizontal scaling, distributing the load across multiple smaller machines. Distributing load across multiple machines is also known as a shared nothing architecture. A system that can run on a single machine is often simpler, but high-end machines can become very expensive, so very intensive workloads often can't avoid scaling out. In reality, good architectures usually involve a pragmatic mixture of approaches. For example, using several fairly powerful machines can still be simpler and cheaper than a large number of small virtual machines. Some systems are elastic, meaning that they can automatically add computing resources when they detect a load increase. Whereas other systems are scaled manually, a human analyzes the capacity and decides to add more machines to the system. An elastic system can be useful if load is highly unpredictable, but manually scaled systems are simpler and may have fewer operational surprises. See rebalancing partitions on page 209. While distributing stateless services across multiple machines is fairly straightforward, taking stateful data systems from a single node to a distributed setup can introduce a lot of additional complexity. For this reason, common wisdom until recently was to keep your database on a single node scale up until scaling cost or high availability requirements forced you to make it distributed. As the tools and abstractions for distributed systems get better, this common wisdom may change. At least for some kinds of applications, it is conceivable that distributed data systems will become the default in the future, even for use cases that don't handle large volumes of data or traffic. Over the course of the rest of this book, we will cover many kinds of distributed data systems and discuss how they fare not just in terms of scalability, but also ease of use and maintainability. The architecture of systems that operate at large scale is usually highly specific to the application. There is no such thing as a generic, one-size-fits-all scalable architecture, informally known as magic scaling sauce. The problem may be the volume of reads, the volume of writes, the volume of data to store, the complexity of the data, the response time requirements, the access patterns, or usually some mixture of all of these plus many more issues. For example, a system that is designed to handle 100,000 requests per second, each 1 KB in size, looks very different from a system that is designed for 3 requests per minute, each 2 GB in size, even though the two systems have the same data throughput. An architecture that scales well for a particular application is built around assumptions of which operations will be common and which will be rare, the load parameters. If those assumptions turn out to be wrong, the engineering effort for scaling is at best wasted, and at worst counterproductive. In an early-stage startup or an unproven product, it's usually more important to be able to iterate quickly on product features than it is to scale to some hypothetical future load. Even though they are specific to a particular application, scalable architectures are nevertheless usually built from general-purpose building blocks, arranged in familiar patterns. In this book, we discuss those building blocks and patterns.